Next speaker is Pierre-Francois Loos from University of Toulouse. So he's going to talk about the many-body Green's function and state-specific CI methods for excited state. So let's welcome Professor Loos.
Let's try this. Okay. That's okay. Can you hear me okay? Yeah. Okay, thank you very much. So yeah, sorry, I changed my title a little bit. I think it was more convenient to talk about this. Sorry, I think in France it's 4 in the morning, so I'm starting to feel it a little bit. I'll try not to fall asleep. Yes, so what I would like to talk about today is many-body perturbation theory. So by this, I don't mean like perturbation theory, I mean Green's function methods. And so those methods are quite new, at least in chemistry. And if you don't know them, well, I'll try to connect that to methods that are much more known in quantum chemistry, that are couplet cluster methods that Piotr talked about and Daniel as well this morning. So before diving into this, I'd like to talk a little bit about RPA, random phase approximation physics. So RPA is a quasi-bosonic approximation, which means that what you're going to try to do is to treat products of fermions as bosons, okay? So it's not exact, so that's why people say that it's a quasi-bosonic approximation. And if you are looking at the particle Hall channel, which is the one that we usually do in electronic structure, because it's more appropriate, but you don't have to do that. Usually what we do is that we treat excitations and de-excitations, the product of those ones, fermionic, as bosons, okay? So in terms of Feynman diagrams, you can show that it's a very clever resummation of diagrams. So what you can see is that if you take, for example, the uniform electron gas, and you want to do like vanilla perturbation theory, you're going to have trouble because each of the order is going to give you infinity, which is never very nice in a program, as you know. But Gelman and Bruckner have shown that if you grab just one piece of each order and you resum all those orders to infinity, you get a finite number. And this is what is RPA actually. And for the students in the room, I'm sure that we have students here. If you've never read this paper here, I really highly recommend this. It's an absolute beautiful piece of work. Okay. Okay, so RPA is nice, and we know that we can use it, for example, to catch long-range correlation, like dispersion. It's been done a lot in the literature, and that's basically what is nice. But most of the times now, what we want is to go beyond RPA, because a quantum chemist, when he has something, he always wants to go beyond anyway. And so today I'd like to talk about the Bethe-Salpeter equations formalism that I'm going to call BSE. And actually, you can see BSE as a very cheap and efficient way of going beyond RPA physics. And it's been used now in solid state physics, for example, in VASP, but also in molecules, okay? The problem is that, well, it's not actually a problem, it's a feature, I'd say, is that BSE is based on what we call a GW calculation. So it's basically you have a protocol, a well-defined protocol, where you're going to do first a GW calculation, and we're going to talk about what is a GW calculation, and after that you can do a BSE calculation. And the Bethe-Salpeter, the GW calculation is going to give you what we call the quasi-particle energy, that are orbital energy that are renormalized or dressed, okay, and what we call the dynamical screening, W, which is a screened version of the Coulomb operator, okay? And here again, you're going to have some dressed correlation at the one body for the quasi-particle energy and the two body with the dynamical screening, okay? So W is obtained via RPA, actually. It's the RPA polarizability, okay? And the idea is that GW is going to give you a very good, what we call fundamental gap, which is the difference between the IP and the EA of the system. And you're going to catch the remaining excitonic effect, okay, via the Bethe-Salpeter equations. So if you want an idea of this, so that's a little scheme that I usually show. So, so you start with, for example, you can start with a Kohn-Sham orbitals and Kohn-Sham orbital energies. And usually when we know that the Kohn-Sham gap is too small for obvious reasons most of the time. And what GW is going to do, GW is a correction on top of Kohn-Sham, okay? It's going to give you a fundamental gap here, which is just the difference between the ionization potential and the electron affinity. That is much closer to the real gap, to the true gap, okay? The problem is that if you want to catch optical excitation, so excited states with the same number of electrons, well, if you have created a hole here, it is a plus charge, and you have put an electron in the conducting band, well, actually, it's a two electron process. It's a plus and minus charge, so they're going to attract each other. So the optical gap is always going to be slightly smaller than the fundamental gap due to its attraction, okay? And that's what you're going to get from the two-body Green's function that is the central quantity of the BSE equations, okay? So that's basically the idea behind the Bethe-Salpeter equations, okay? So that's nice, and that works very, very well in practice. You can get some very good results, very, very cheap for molecules, but there is some shortcomings as well. And one of them that I'd like to talk about today is that the main one, actually, in that context, is that actually computing the exact, the total energy at the BSE level is not something super well defined, and most of the time it's quite tricky to get. Okay, so I guess you can understand if I struggle to define the energy, I'm going to struggle to compute the properties that are derivatives of the energy, okay? And the main problem behind this is that if you want to use BSE for photochemistry, you really need to be able to compute those properties. So it's really going to hamper the applicability of BSE into photochemistry, okay? And that's what we want to solve here. So we'll try to find another way of fixing that issue. And so, for example, we know that couplet cluster is a very mature theory, and I'm pretty sure most of you are going to agree with me. And we have a very well-defined route to get properties through the lambda equations that we saw just before, okay? And so basically the idea of this talk is to try to link BSE GW to the couplet cluster equations so that to be able to transfer all the technologies that we have developed for 40 or 50 years in couplet cluster to the many body perturbation theory methods, okay, Green's function methods. So that's the idea. So how can we do this? Okay, so if you're looking more closely into the BSE equations, you're going to be surprised because those equations here, that's the equation that you're going to solve for Bethe-Salpeter, okay? So they are basically Cassidy-like equations. That's basically the same equations that you would solve for TDHF, TDDFT, whatever you want. They are always the same thing. So the main differences in those equations is the way you're going to compute those matrix elements, okay? So here, if I was doing TDDFT, I would get like Kohn-Sham energies, and here I've got GW one electron energies, where I've already have correlation that are dressed into those orbital energies, okay? And here as well, the second features of those equations is that I have some effective two-body terms, like in the equations of motion couplet cluster methods, if you want. So I have my R3 in exchange term, exactly like TD R3 fuck. So I have 100% of exact exchange, if you want to talk DFT. But I have a correlation here, a correlation part that comes from the screening, the static screening coming from GW, okay? So same equations, but I replace my exchange correlation kernel from TD-DFT with 100% of R3 fuck exchange, and I add some correlation coming from GW. That's it. So it's basically a TDHF type system with where I've already dressed some correlation at the one body and two body level. Okay, that's it. And so if we want to link this to couplet clusters, so we can use a very nice paper by Scuderia and co-workers. Okay, so if you assume that x, so x and y are the eigenvectors here, and here I have the eigenvalues. Okay, so if I assume that x minus 1 exists, which is true if your system is stable. So if it's not stable, you have way around it. It's not a problem. So you can actually recast those equations here by multiplying by x minus 1 on the right. You end up with that type, with that system. And if I write down the two lines of that system here, and I substitute these first equations into the second one, I end up with a Riccati equations. That's something that has been shown by Scuderia a long time ago now. And that's something that is exact, okay? And if I take that Riccati equations and I write it down if I write it down explicitly, what you can show is that it gives you a subset of the CCD equation, couplet cluster with doubles, okay? And that gives you what we call the ring diagrams or the ring terms of the couplet cluster equations. So you can rewrite the BSE equations as addressed ring CCD amplitude equations here. And from this, because now you have a couplet cluster system of equations, you can actually write down very, very naturally the energy of that system. Okay, that's basically given by the trace of B times T with a quarter. And you can show with the invariance of the trace that it's also equal to what we call the trace formula that we use in RPA to calculate the correlation energy RD RPA level. So basically what you can show, sorry, I'm going to try to move this. What you can show is that BSE at GW is equivalent to a dressed ring couplet cluster problem, okay? And so there is a direct connections between the two, but you need to use those dressed one electron energy over there and those dressed two electron integral over here, okay? And for the people who know similarity transform equation of motion couplet cluster, that's basically roughly the same idea behind this, okay? So we can talk about it later, okay? Sorry. Okay, so that's nice because it gives us a route to actually compute the gradients if we can compute the lambda equations, okay? And we know that we can compute the lambda equations for ring CCD. So it's been shown by the work of Rishi, who's from the Bartlett group. But can we go further than this, and can we try to link GW as well from two couplet clusters? So I take this opportunity to talk a little bit about GW because I think it's a new method in quantum chemistry. And GW, so it's actually a byproduct of what we call the Edin's equations. Okay, Edin's equations, what it is, it's based on what we call the Edin's pentagon here. And the idea of Edin's pentagon, it's quite beautiful, is that if you come in with a set of orbitals and energy here, okay? It can be R3 it can be conjoined, it can be non-interacting energy if you're really poor, okay? And you actually iterate 5 quantities, you're going to get out with the exact IPs and EAs of the system, okay? So what you have to do, you have to link, so you have a set of 5 equations that link the Green's function, the vertex function to the polarizabilities and polarizability, the screening, and the self energy, which is really the central quantity of the GW methods. Okay, so you have to iterate those equations. They are horrible. Okay, they are nonlinear, highly nonlinear. You have integrals, derivatives, and so on. You don't even know in which way you should iterate them. You can iterate them one way or another way, and depending on the way you iterate, you might end up on a different solution. So it's horrible. And so I didn't say, okay, maybe it's too difficult. And actually, the tricky guy is the vertex correction here. Okay, and you see that vertex correction has two terms, and the first term here is very simple. So you say, okay, so what we're going to do is that we're going to approximate that vertex function by the first term. And lucky us, the first term is just a bunch of delta functions. And so basically by doing just this, so you transform your pentagon to a kind of a square, okay, which is a much simpler square. And so you can show that the polarizability is just G squared, W is just a PW, and you end up with an expression for sigma that is just GW. So it's the convolution of the Green's function and the dynamically screened Coulomb potential. And that's why it's called GW, because sigma is given by the product of G and W. Okay? So that's the idea. Okay, so the GW equations are a little bit peculiar because they are what we call frequency-dependent equations. So they are nonlinear. You have to solve them iteratively. It's quite annoying. Okay, but you can do it. So so there is many ways of solving the GW equation. There is what they call the one-shot G0W0. There is EVGW, QSGW, and so on. But that's in the most like general setup. Basically, what you have to do is that you have to solve that type of equation. So that's a nonlinear eigenproblem, if you want, okay? Because your self-energy depends on the eigenvalue as well, okay? So that's nonlinear. That's an effective Hamiltonian, if you want. And you know that if you have an effective Hamiltonian, you can always rewrite that set of equation as a larger set that is linear. That's what we call the folding, downfolding, upfolding process. And so basically, you can rewrite those equations here as a set of nonlinear equations over here, where you have much more physics, okay? But they are slightly more expensive as well, okay? And what we can show here is that basically, in GW, you have an explicit explicit configuration that comes from the 2-1P and the 2P1-all configuration, okay? And so now that we have a matrix form here, well, what we can do is that we can apply the same process as before for BAC to link it to GW. And basically what we can include, so that's basically an EOM version of GW, quotes. It's not exactly this, but you can see as an effective Hamiltonian in a CI basis, okay? And if you again define that those GW amplitudes now, okay, so it's not going to be like 2-all 2P amplitudes, it's going to be 2P1-all and 2-all 1P amplitudes. Well, actually now you can recast those equations, okay, as two coupled Riccati equations, okay? So basically that will be like in CCSD where you have one Riccati equations for the T1 amplitudes and one Riccati equations for the T2 amplitudes, okay? So here you have two Riccati equations, one for the 2-all 1P sector and one for the 2P1-all, and they are coupled together, okay? So they are coupled together because you don't have all the diagrams in GW. You're missing some diagrams, and so you coupled the sectors of the Fock space. So that's something that is quite peculiar because in EOM couplet cluster, you wouldn't get that. Okay, if I have this, I can rewrite that as amplitude equations, exactly like couplet cluster. And I can use the usual process of couplet cluster to actually, so the iterative process, we are refine my amplitudes via like a quasi-Newton process to get my quasi-particle energy. So basically, you can recast. So the conclusion here is that you can recast again the GW equation as a set of couplet cluster-like equations. And basically, here you won't compute an energy, but you will have to diagonalize a matrix that is much smaller than your bin matrix, where the self energy is going to be given by the product of your amplitudes times your coupling vectors. Okay, and now you can iterate exactly like a couplet cluster code. So if you have a couplet cluster code, now you can do BSC and GW with very, very few modification of your code. And that gives you, again, a well-defined way to compute gradients and doing photochemistry and so on. All right, so just to conclude, so here I wanted to show that there is potential. So this new way gives you probably a way to go beyond what we can do at the moment for BSC GW, to get like ground and excited state properties at that level, to make it like more applicable to photochemistry. As you know, if you want gradients at the couplet cluster level, you have to be able to compute the lambda equations, okay, because it's a non-variational technique, but you can do that as well. There is not much problem doing this. And actually, you might actually use what we know in multi-reference couplet cluster theory to apply that to GW to be able to develop like multi-reference GW methods. And we're looking into this at the moment. And just to finish that thing, so all those things are being implemented in our open source software, Quantum package that we develop in Toulouse and in France more generally. And everything is available online for free. And thank you for your attention.
Okay, thank you. Any question? Okay.
So the formal scaling of BSC GW is rumored to be in the 6th, so that must not come from the RPA equation. It must come from computing the kernel W. RPA is in the 6th only if you need all of the eigenvalues.
That's right, exactly.
So it's the W kernel is in the 6th.
Yes.
Okay.
So.
And was that because of the CCD type contractions? I was trying to follow it through, but I couldn't.
No. So if you talk about the scaling of GW, the computational bottleneck is the calculation of the RPA polarizability. Exactly as you said. Why? Because to get the polarizability, you need the entire spectrum. So you need to compute all the eigenvalues and all the eigenvectors of your RPA matrix. But people have found a way around that, because you can use like contour deformation techniques and compute W in the complex plane, and you can lower that cost to NQ. But that's very technical.
That's sort of changing the creep factor.
No. You change the real scaling. Yes. So there is two types of GW code out there. There is people that compute the polarizability like me, n to the 6, and that's definitely the bottleneck. And people that are doing stuff in the complex plane to make it cheaper.
Okay, so your trace equation, that's computing polarizability.
Yes.
Okay.
That's the most expensive part. If you want to compute.
So you're effectively diagonalizing the full RPA matrix.
And people have tried to do many different approximations on this, and there is no way. You have to compute the entire spectrum because what you're trying to get is something that is very broad and spread, and there is no way you're going to get that by calculating the first 10 eigenvalues on the map. And I don't know if you know, in solid state, for example, they use displacement pole approximation, where they basically, so that was a way around that, saying like, well, I have my big like Gaussian shape kind of thing, and I use that as my polarizability. But if you want the total energy at the BSC level, it's also n to the 6. But if you want only optical excitations, it's n to the 4, because you don't need to compute all the eigenvalues. But you still need to do the GW calculation first. So
Okay, so we have other questions from online audiences. So Professor Piotr Pierre-Kuchi, you have a question, right? So please go ahead.
I can also see Michael. I don't know if Michael wants to ask the question first.
First? Oh, okay. Right. Thank you. Thank you, Piotr. I have a question about application of PST and GW methodology in general to multi-configurational systems. In epsilon and psi, GW are in essence Dyson's orbitals.
Yes.
In GW approximation, right?
Yes, you can say that. Yeah.
Dyson's orbitals are not necessarily normalized to unity. For multi-configurational or open shell systems, they will be normalized to something between 0 and 1.
Mhm.
How will you
Yes.
approach
Yeah.
these?
Well, so to be fair, like BSCGW, normally it's not something that should be used for multi-reference system because that's theory that's developed for a well-defined kind of single reference method. So, and it's for weakly correlated system because everything is a perturbation expansion in terms of W. Okay. So if you go in strong correlation, you're going to step out of the idea behind the methods, because the methods resemble a certain type of diagrams, and we know that those diagrams are crucial for weakly correlated system, but we know that if you go strongly correlated, that's not the type of diagrams that you should resum. But you can use maybe something else. For example, there is what we call the T-matrix approximation. That's resum the ladder diagram instead of the ring diagrams. That might be more suitable for those systems. So you have to be a little bit careful here.
Yeah, definitely. But maybe I'm wrong here in my expectation, but ring CCD is in some sense equivalent to GVB, perfect pairing.
I don't know. I don't know.
Because if it is, then ring CCD should be perfectly capable of capturing the multi-reference effects, like GVB does.
Well, ring CCD is only the ring diagrams, direct on exchange. So I don't see how it would be equivalent to GVB, but I have no knowledge on this. So I prefer not to comment.
Right. Thank you.
Okay, then Professor Piotr Pierre-Kuchi.
Hi, Pierre-Francois. Nice lecture. So
Hi.
I have, I guess, two questions. One question would be, so I was looking at your equations, and I'm sure I missed something, but essentially you are restricting these equations to 2-particle one hole and 2-hole 1-particle type terms, right? And I appreciate that, of course, that keeps the cost low, but you know, I never did Green's functions directly, but we have experience with equation of motion, and for electron attached or ionization potential type methods,
Yes.
the minimum level which is acceptable is 3-particle 2-hole and 3-hole 2-particle. That's my experience. Now, is this relevant to your work? Would you be thinking about including them, or you don't think that you need them?
So yes, I see what you mean here. So if you do, so the idea of GW is to have something that is very, very well as cheap as possible. Okay,
No, I appreciate that, but you know, in terms of the underlying, you know, physics, let's forget the cost for a second, and
yes,
in terms of what is that you need to get a reasonable description.
So the thing is that in equation of motion, IP and EA, your IP and EA sectors are decoupled. Okay, do you agree with that?
Yes, I do.
Okay, so in GW they are not decoupled. Okay, and you see, for example, in the matrix that is here, that you have an interaction, for example, between the 1-hole and the 2p1-hole sectors, and between the 1p and the 2-hole 1p. And so that's the same idea as in ADCs, that those couplings actually create terms that are higher than 2-hole 1p and 2p 1-hole. And it's explained in Schirmer's book, for example, is that if you do a CI expansion, with those extra coupling, you can show that those extra coupling that could be seen as unphysical because they couple different sectors of Fock space, they actually have the effect of creating higher degree. So they're going to create 3-all 2p and 3p 2-all terms.
Okay.
And so
it's more like
that's part of the magic.
So it's part. So in that way, that is probably more similar to the Fock space kappa cluster, which actually mixes all these things together.
Exactly. Yeah. Yes.
Okay.
And it makes the expansion more compact as well.
Right. So the second question would be kind of, I guess, I don't know how to say, so there's this effort by, right now, there's also this resurgence in this kappa cluster Green's function, like Kowalski and I think Dominica's Git, perhaps. I mean, so how do you compare what you're doing here with what they do?
Yeah, well, so it's not quite the same here because so basically they want to compute like spectral function with couplet cluster, I think. But really what they do is very similar to STEOM couplet cluster. So it's a different way of approaching the problem, but they still use all the diagram of couplet cluster to compute properties and so on. So here is just that we do one part of the diagram. So yeah, I think it's very different actually, but I might be wrong, but I think it's different.
Okay, thank you very much.
Thank you.
Okay, then let's end the session. So let's thank the Professor Loos again and all the other speakers for very interesting talk. Okay, now it's lunchtime.
Okay, yeah, we have a plan of time. Please come back at 1:40, right? So we have 1 hour and 10 minutes for lunch. To pick up your lunch box back there. You can enjoy your lunch. Okay.
One active basis, the size of this, how fast it converges to basis size. Do you know? Or not?
You mean like it's exactly like in couplet cluster. This is we still have a sum over the virtuals. So this sum over the virtuals, like in MP2, it's conversion 1 over L cubed.
So if you get accurate results, you really have to
Yeah.
get a huge base.
Yes. Yeah. So
That could be hard.
Yeah,
It's like couplet cluster.
it's exactly like couplet cluster. It's the same problem. It's the cusp doesn't converge very well. So you have to use, you can use the same tricks. But,
I think more.
yeah, no problem.